Now in this class you will see belt drives, ratio of driving tensions for flat belt drive. So this topic, it is there for mechanical engineering, BE mechanical engineering syllabus. It is there for mechanical engineering students, for automobile engineering students, for aeronautical engineering students, and also BE marine engineering students. So this is a common topic. It comes under theory of machines or mechanics of machines, whatever it is. So ratio of driving tensions for flat belt drives. So here this is a flat belt which is used for power transmission between two parallel shafts. It is used in machine shops, it is used in industries, etc. When the two shafts are parallel and the distance is up to 10 meters, these flat belts are used to transmit power. So it is necessary to determine the driving tensions in the belt. So here this is the pulley for the belt drive. This is a driven pulley, that is follower pulley, right? This is the belt drive. So this is the belt which touches here. The belt touches at point D, touches the pulley, and it leaves at point C, right? Therefore this is the angle of contact or angle of lap, right? The angle subtended by the belt to the center of the pulley. This is called angle of contact or angle of lap. This is a driven pulley. This is the direction of pulley rotation. This is the shaft, pulley shaft. So here, this is the tension on the tight side of the belt, because the belt is pulled and pushed like this. Therefore it is pulled and it goes to the other pulley and it comes like this, right? It is pushed. Therefore this is the tension on the tight side of the pulley. Tension on the tight side, T1. It is a force, tension force. T2 is the tension force on the slack side of the belt. So tension on the tight side, because it is pulled here, tension on the tight side is more than the tension on the slack side. Therefore T1 is greater than T2, right? So here you see this is the angle subtended by the belt to the center of the pulley. Theta is the angle. That is angle COD is theta. Right. Now consider a small portion of the belt here. This is the LM of the belt, small portion LM of the belt. This small portion is subjected to following forces. Tension T at point L, tension T plus del T at point M, and normal reaction Rn exerted by the pulley on the belt, and friction force F is equal to mu into Rn. Friction force, because the belt, the belt, it goes like this, the pulley rotates like this, the belt goes right in this direction. Therefore the frictional force is in the opposite direction, in this direction, the frictional force. This is the force of friction, right? So here the portion LM of the belt is under the following forces, that is the force of friction, tension T at point L, tension T plus del T at point M. Now this is the del theta is the angle subtended by the small portion LM of the belt with the center. This is the angle del theta, LOM is del theta. Right. Now we draw the forces in the coordinate system. Now here I separately draw this portion LM here, right? This is T, tension T, force F, frictional force F is equal to mu into Rn. Rn is a normal reaction, and this angle is del theta by 2, this angle is del theta by 2. Here del T plus del T. Now how I superimpose these forces in the coordinate system, right? So this is the force of friction F, this is the normal reaction Rn, this is the tension T plus del T. This angle is del theta by 2, because this is del theta by 2, this is del theta by 2, therefore this should be del theta by 2 and del theta by 2. So these are all the forces acting, right, on the small portion of the belt. Right? We have to find the ratio of the driving tensions, that is driving tension T1 and T2 are the driving tensions. We'll see. Consider a small portion. It subtends an angle del theta at the center. So the belt is in equilibrium under the following forces. Tension T in the belt at L Therefore, belt is in equilibrium under the following forces: under tension T in the belt at L, tension T plus del T at M, normal reaction at Rn, frictional force F is equal to mu into Rn. Solving the forces horizontally. Resolving the forces horizontally, sigma h is equal to 0. Sum of the horizontal forces is equal to 0 because it is under equilibrium. Therefore, horizontal component here, Rn, horizontal component here, this is Rn. Here, horizontal component of this is, right? So, this is T into sine minus T plus del T sine del theta by 2, because this is the force. Horizontal component is T plus del T sine del theta by 2. Horizontal component acts in this direction, right? This horizontal component acts in this direction. Both are towards left, therefore negative. T plus del T minus sine del theta by 2 minus T sine del theta by 2. Rn is towards right, therefore it is positive. Equal to 0. Sine del theta by 2 is very small, therefore instead of sine del theta by 2, I can write del theta by 2. Therefore Rn, I take this to the right side, therefore I can write T del theta by 2 plus T del theta by 2. I can take this to the right side, it becomes like this, right? Sine del theta by 2 is very small, multiply inside, see T sine del theta by 2, right? Sine del theta by 2 is small, therefore I write T del theta by 2. Del T sine del theta by 2, del T and del theta by 2 are small, therefore that is 0, you can neglect that. Then it becomes again T sine del theta by 2, take this to the right, it becomes T del theta by 2. Therefore, Rn is equal to T del theta, right? Resolving the forces vertically, You can write vertical. What are the vertical components? F plus T plus this is plus T cos del theta by 2 minus T plus del T sin del theta by 2. Therefore, F plus upward force positive. F plus T cos del theta by 2 minus of T plus del T cos del theta by 2 equal to 0. Right? Therefore, cos del theta by 2 is very small. Therefore, you can take cos 0 is 1. Therefore, it is 1. Cos del theta by 2 is 1. Right? Therefore, F plus T. Here, minus of, right, T plus del T. Because cos del theta by 2 is 1. So F plus T minus T plus, minus del T is equal to 0. T cancels. F is equal to del T. Mu Rn. F is equal to mu Rn. We know that mu Rn equal to del T. Now substitute the value of Rn here in this equation. Already we have found out. Mu into T del theta Rn equal to del T. Therefore, del T by T is equal to mu del theta. Integrate both sides. Integrate T to 2 because lower tension is T1, T2, higher tension is T1. Del T by T is equal to integral mu del theta. Therefore, I can write log del T by T, log base E T, T2 to T1 equal to mu into theta. Integral del theta, theta mu is constant, right? Therefore, substitute here the different integral log T1 base E minus log T2 base E equal to mu theta. Therefore, logarithm of T1 by T2. Use logarithm. Base E equal to mu theta. Therefore, T1 by T2 is equal to e power mu theta. So this is the ratio of the driving tensions in the belt drive. T1 by T2 equal to e power mu theta.